Related rates is one of those topics where if you are comfortable with calculus and about keeping track of which quantities are variable and which quantities are fixed, isn't really that bad. The challenge comes in the very act of keeping track of what is what and in some of the geometry that is involved, because quite a few related rates problems turn out to be geometric. Let's just take a look at a problem that is part of this class of problems and then see how we would solve these problems in general. So take a spherical balloon that is being filled with helium at a rate of 2 cubic feet per second, and we want to know at what rate the radius is changing when the volume of the balloon is 3 cubic feet. Now, I think just about any kid has inflated a balloon at some point in time, not necessarily with helium, but one of the things that we do know is when you blow up a balloon, at first the radius grows rather rapidly and then it slows down as the balloon gets bigger. Okay, so independent of all other formulas, quantities in this problem will depend on time. So that's an underlying variable. That's the first thing we have to acknowledge and then keep track of. And well, other than that, we need some formulas. We need the volume of a sphere, which is 4/3 pi r cubed. That's one of those formulas you've just got to memorize it. I don't know any good way of skirting memorizing that formula. So yep, memorize it, know it. And r is the radius and v is the volume, and they both depend on time. And the key insight to related rates then is that equal functions will have equal derivatives. So if v of t is equal to 4/3 pi r of t cubed, right? That's what it would be if we wrote it out completely and explicitly. And this is then also sort of like what you would do in implicit differentiation, because in fact implicit differentiation is underlying to related rates. Well, if we have that and we take derivatives on both sides, well, then we get derivatives on both sides. And let's see, what would we get? We would get dv dt is 4/3 pi times 3r squared times dr dt, right? That's the part that is always important. That's the part that we had to get used to in implicit differentiation, that we had to still multiply with the derivative of the inside, and that's the case here also. Okay, and yeah, you simplify that, that's 4 pi r squared dr dt, which means, well, what are we interested in? We're interested in the rate at which the radius is changing, so we're interested in dr dt, so we solve for dr dt, that's 1/4 pi r squared dv dt, and well, that means now we can just plug in the numbers. 3 cubic feet is the volume, right? We have to find the radius too, right? Because if we're looking at what we had here, we need r and we don't have it. Okay, well, we can find that. 3 cubic feet is the volume. The volume is 4/3 pi r cubed. That means 9/4 pi cubic feet is the cube of the radius, and the radius is the third root of 9/4 pi cubic feet, which is the third root of 9/4 pi feet. Units work out. Good sanity check that our computation ought to be at least reasonable so far. And therefore, well, therefore, dr dt when the volume is 3 cubic feet is dr dt when the radius is that third root of 9/4 pi times feet, which is 1/4 pi radius squared times the 2 cubic feet per second. And if you work that out, let's see, I did simplify that a little bit. Yeah, okay, well, I did cancel the 2, and the third root squared is an exponent 2/3. Look, I mean, and much more importantly, the square feet in the bottom cancel with the cubic feet on the top, and so we end up with feet per second, which is what its rate of change for the radius should be. And well, then we also get a number. It's 0.1988. Okay, yeah, I mean that's just a number. All right, so what did we do here? Well, we determined the independent variable, and that was time. We determined which of the involved variables were functions of the independent variable, and that was all of them. We only had volume and radius, and they're both dependent on time. We marked them as functions. You only do that if you really want to be sure, and certainly at the beginning it's recommendable that you want to do that. And then we needed to find an equation that relates the variables to each other. That was the volume equation. If possible, a picture should help. Well, here you really couldn't draw a picture. We'll see a geometric example where you can in just a little bit. And then you differentiate with respect to the independent variable. You solve for the desired quantity, which may well be a rate. and then you substitute values for the quantities whose values are known, and well, that's how you solve related rates problems. The um, the devil is in the details. It's just like optimization problems. You really have to think about what kinds of formulas you have to use. You may have to derive some formulas, and you have to keep thinking of the meaning of the various entities in the formulas. But also note that unlike for optimization problems, there really is no obvious tip that we're working with related rates. I mean, in an optimization problem, find the best, find the maximum, find the minimum, find the optimal, that kind of thing tells us what we have to do. For related rates, yeah, okay, maybe the question that you're looking for a rate is a tip-off. Okay, so example, let's take a look at the example we had one more time in terms of this framework that we have now. So we've got this balloon that is filled with helium at a rate of 2 cubic feet per second. At what rate is the radius changing when the volume is 3 cubic feet? And let's take 2 of the whole thing. The independent variable is time t. The dependent variables are volume depending on time and radius depending on time. The equation is the equation for the volume. The derivatives give us what dv dt is, and if we solve for the quantity that we're interested in, we get an equation for dr dt. Then we substitute values, but note that we had to compute the value for r first, so sometimes you have to do some more algebra, and that gave us dr dt at v equals 3 cubic feet was ultimately the 0.1988 feet per second that we computed there. All right, so that was just a review. Let's take a look at a geometric example. A 6-foot tall man is walking away from a 9-foot tall lamppost at a rate of 5 feet per second. How fast is the man's shadow growing when he is 4 feet away from the post? So obviously that is a mathematical toy problem. The situation certainly is realistic, because as you walk away from the streetlight, your shadow is getting longer, and you could wonder how, at what rate that shadow is getting longer, but it certainly is not an applied problem. So here's a guy going shooby-dooby-dooby-dooby-dooby-doo as he's walking away from the lamppost. Okay, maybe he's not singing, but what we can see here, certainly in this animation, is that the shadow is getting longer as the guy is walking away from the lamppost, because the rays of light that are blocked out by the man are hitting the tangential rays that are tangential to the top of the head are touching 2 points that give a flatter and flatter slope as we are looking at this situation. Okay, now the other thing that this shows is that even if you can visualize this stuff moving, that really doesn't help that much. So let's draw a picture. So here's the flat ground, here's the lamppost, here's the guy, and the length of the shadow is determined by the first ray of light that barely hits the ground, because that's where the shadow ends. And so then the length of the shadow is this, that's s of t, because it depends on time. Then the distance from the man to the lamppost, that's p of t, I guess for post. Then we have to remind ourselves that the man is walking, so dp dt is 5 feet per second. It's increasing, as we have seen in the last picture. And, well, the total distance from the post to the end of the shadow, we'll call that x of t, because we want to talk about some things in similar triangles. What else do we have? We have that the man is 6 feet tall, and we know that the post is 9 feet tall. So now from the definition of the tangent function, we know that 9 feet to x is the same as 6 feet to s, right? So 6 feet to s is the same as 9 feet to x. Okay, well, 9 feet to x is 9 feet to p of t plus s of t, because we really don't know how x of t changes. We just know that it's p of t plus s of t. And so that's what we can play calculus with now. 6 feet to s is 9 feet to p plus s. That means s over 6 feet is the same as p plus s over 9 feet. So that means s over 6 feet minus s over 9 feet is p over 9 feet. We solved, well, we brought everything with s to one side. And 1/6 minus 1/9 should be 1/18. So s over 18 feet is p over 19 feet. That means S of t is 2 times P of t, which also makes sense because this has a length unit and that has a length unit. That means the computation here actually is fairly easy. It's the geometry that can get you in some of these problems, and some problems have complicated geometry and, well, reasonably complicated computations. But now when S is equal to 2 times P, then ds dt is 2 times dp dt, and that is because he's walking at 5 feet per second. That ds dt is 10 feet per second, and that's the end of the presentation. All right, so that was fairly short and sweet. I think that is similar to what you've also seen in optimization problems. Technically speaking, we haven't learned anything new here. We knew the formulas, we knew how to do geometry, and we already knew how to do implicit differentiation, but that's exactly the kind of stuff that is often difficult in calculus, because now we just have to take what we know, synthesize it, and put it together to solve new problems. And then again, that is also exactly why we need to pay good attention to these kinds of problems, because they prepare us for the real life situation when we ultimately have a job. Because yeah, training, on the job training often is still part of it, but in order to actually make money for your employer, so your employer can pay you, you don't get paid to learn. You get paid to use what you know, maybe learn a little bit more, and then produce something that is new, which is exactly this kind of situation. Only that, well, unless you're a teacher, it's unclear whether you will get paid to solve related rates problems. All right, well, I'm done. You're going to do the homework, and then you'll be back for the next one. I'll see you there.